7.4, we're proving trigonometric identities. The goal is to use equivalent trigonometric relationships to prove an identity. An equation is an identity. So what we mean by identity is just usually, or always, if the left side equals the right side. So when Alicia graphs the function sine 2x over 1 plus cos 2x, she finds that the graph looks very similar to that of f at x equals tan x. It's actually identical. So she makes the conjecture that this is in fact a trigonometric identity. So we need to prove that now. How can Alicia prove that her conjecture is true? So we have two sides here. It's your choice which side you start with to try to get to the other side, and usually the pattern is we always start with the more complex side, okay, because tan is already fairly reduced terms. Not much we could do with tan x. So we're starting with the left hand side. So we know, or we should know by now, the double angle formulas. So for sine 2x, we're going to substitute in 2 sine x cos x, and then for cos 2x, we're going to substitute in 2 cos squared x minus 1. Yeah, these are both from 7.3 that we've learned, the double angle formulas. So once we do that, we see that the 1's cancel out, and we're left with 2 sine x cos x over 2 cos squared x. The x's now cancel out, and we're left with sine x over cos x, which we know is, of course, tan x. So the left-hand side equals the right-hand side. Any questions on that one? Pretty straightforward. So therefore we can make the conclusion then, of course, that since both sides are equal, sine 2x over 1 plus cos 2x is equal to tan x. It's important to note the exception that cos 2x cannot equal negative 1, because if it did, the denominator here would be 0. And the other one is cos x can't equal 0. Can anyone tell me why that's the case?
Pardon me, Mr. Kilkenny and Mr. Freitas. Could
Alan?
you please contact the office, Ms. Kilkenny and Mr. Freitas?
Alan?
Is it the denominator?
Right, it's the denominator of tan x. Because tan x we know is sine x over cos x. So if cos x was 0, then this expression here would be undefined. Why was the left side of the identity simplified at the beginning of the solution? Why did we choose the left side? I mentioned it. Yeah.
Because it was more complex.
Yeah, you generally start with the more complex. You can actually work with both sides if you need to, right? If both are complex and you want to reduce them both partially to get to the same value. Which formula for cos 2x was used, and why could another formula have been used? So if we go back to the equation here, here was the value that was used for cos 2x, 2 cos squared x minus 1. Anybody tell me why that one was used? And remember, there's 3 of them, right? Anybody remember? Well, first of all, who remembers the other 2? So cos 2x is equal to
1 minus sine squared.
This is almost correct, because there was something else to this, no? You guys remember?
Oh, 2.
Yeah, thanks. Okay, and there was one more?
Cos squared theta minus sine squared theta.
Right? So we could have used these 2 and substituted in here. Any reason why we chose that one? Yeah?
I don't know, maybe you can see that it can cancel out the 1's.
Yeah, they cancel out the 1's right away. But even if we did, let's say we substituted in, let's take this one, and we substituted in for cos 2x. So we would have had sine 2x over 1 plus okay, now what can we do here?
Can it cancel out sine x?
1 minus sine squared x is what? Cos squared x, right? Because of this identity. right? So this then becomes, we can substitute in here for sine squared x, 1 minus sine squared x is cos squared x. So the top becomes sine 2 sine x cos x, we know, over 2 cos squared x. Any questions up to there? And finally the last part is we cancel
So how did you get that, the 2 sine x cos
from the double angle formula. Sine 2x is 2 sine x cos x. Okay, so it wouldn't have mattered which one we would have used. You also would have got the same answer using the other one if we use this one, okay? C says, if you replaced x with pi over 4 in Alicia's conjecture and you showed that both sides result in the same value, could you conclude that the equation is an identity? Explain. So the answer is yes, right? If we're getting the same value on either side, after we simplify with an angle, we can conclude that it's identity. Example 2, proving that an equation is not an identity. So this is quite a bit easier, right? If they ask you to prove it's not an identity, you just pick a value. In this case, they chose 90 degrees, substitute it in, and they find that the left side does not equal the right side, therefore it's not an identity. So very simple if asked to prove something's not an identity. Using reasoning to prove a co-function identity. So we have now, we want to prove this addition identity. Cos 90 plus x is equal to negative sine x. So we should know this from actually just the graphs themselves and translations of 90 degrees on the graphs. But if we want to prove it algebraically, we can use the addition sum formula. So cos A plus B is cos A cos B minus sine A sine B. So that goes to this formula. Next, we can substitute in the known values for cos 90 and sine 90. So cos 90 is 0, sine 90 is 1, and we end up with negative sine x. Again, very straightforward, very simple. Example 4, using reasoning to prove an identity that involves rational trigonometric expressions. So here's one that's quite a bit more complex. So as we learned last year with trigonometric identities, we have a couple of tools that we can use. One of them is multiplying by 1 and different strategies of multiplying by 1. In this case, we chose cos x cos y over cos x cos y, which again is 1, but we did that in order to eliminate the denominators in both the numerator and the denominator of the original function. Okay, so our tan terms we converted to sine over cos, and then we multiplied both the top and the bottom by cos x cos y over cos x cos y. So what that allowed us to do is cancel out these, and we're left with this numerator over this denominator. We simplify that, kind of a reverse simplification, into the summation and subtraction formulas for cos. Should recognize that this pattern is actually equal to cos x minus y, and this pattern here is cos x plus y. Yep.
How did you get the symbols for cos x plus sine x, sine x? How did you get that? Yeah.
This?
Yeah, because you know first they were being multiplied, and then how did you get those symbols?
Oh, okay. So cos x cos y times 1 is cos x cos y, right?
Yeah.
and then cos x cos y times this, it's like this.
Oh.
You see how they cancel?
Yeah.
So you're left with sine x sine y, okay? That's example 4. And finally, just to conclude, since we ended up with the same answer that we started with, we know that this is in fact a trigonometric identity. Again, important to point out that you have to make these exceptions where cos x plus y is equal to 0. Hi there.
Hi, is Luigi Giuliano in class?
No.
No? Did
No.
he leave?
He's not here.
Not there, okay.
Okay, so the last example, example 5, prove that tan 2x minus 2 tan x tan 2x sine squared x is equal to sine 2x. So again, we'll start with the more complex side, the left-hand side. And we're going to try and use the formulas that we know. The first strategy we use actually is we notice that tan 2x is similar. It's in both terms, so we factor out tan 2x. Okay, so that's from here to here. Tan 2x, we divide both terms by tan 2x, we get 1 minus 2 sine squared x. Once we do that, we recognize that 1 minus 2 sine squared x is actually cos 2x, which we talked about in the first example. And then when we substitute tan 2x for sine 2x cos 2x, we're able to make a cancellation there, and we end up with sine 2x. Again, quite straightforward. In the denominator, we have to specify that cos 2x cannot equal 0. So since both sides are equal, we have this identity. Any questions with that one?
So how do you put the restriction? How do you find that out?
How do you put the restriction?
Yeah, like how do you find out the restriction?
Oh, because the denominator can't be 0. That's how.
Oh, okay.
Okay? So there it can't be 0. And the other one here, cos x plus y can't be 0 because it's in the denominator. And tan x plus tan y can't be 1 because it would be 1 minus 1. Okay? Alright, in summary, a trigonometric identity states the equivalence of two trigonometric expressions. It is written as an equation that involves trigonometric ratios, and the solution set is all real numbers for which the expressions on both sides of the equation are defined. As a result, the equation has an infinite number of solutions. It's infinite because these are all trigonometric identities, so they're a repeating pattern that goes on for infinity. Some trigonometric identities are the result of a definition, while others are derived from the relationship that exists among trigonometric ratios. The following trigonometric identities are important for you to remember. So here's your reciprocal identities, which we've known for a long time. Quotient identities, same thing. Pythagorean identities, these were all learned last year. And then these are our new identities from grade 12. You can verify the truth of a given trigonometric identity by graphing each side separately and showing that the two graphs are the same. To prove that a given equation is an identity, the two sides of the equation must be shown to be equivalent. This can be accomplished by using a variety of strategies. So simplify the more complicated side first until it's identical, or manipulate both sides to get the same expression. So if you get stuck on one side but you've taken it some distance, maybe start with the other side. You can rewrite the expression using any of the identities stated above. So you use these identities to help simplify. And finally, you either use a common denominator or factoring when possible. The common denominator is when we multiply by 1, and factoring is when we take out a like term. Okay, any questions?